In this video, we're going to look at the second factor that we consider when we're assessing the relative strengths of a set of bases, and this is what we call inductive effects. In the last video, I showed you the difference in the pKa's of trifluoroacetic acid, which you see in the bottom left in green, and acetic acid, which you see on the bottom right in blue. And we also learned in the last video that there are factors that we use to assess the relative strengths of bases to be able to make a statement about the strengths of their conjugate acids. So since trifluoroacetic acid is a stronger acid than acetic acid, we know this from the pKa values, we can conclude that the conjugate base of trifluoroacetic acid on the upper left is a weaker base than the conjugate base of acetic acid, which is up on the upper right. But again, this gets confusing because we don't really know why. So we're going to look into this set of acids a little more closely. Let's do a comparison of the conjugate bases of trifluoroacetic acid and acetic acid. The difference in the relative stabilities can't be accounted for based on elemental effects because in both cases we have a negatively charged oxygen. But what is different between the two is that on the left, the trifluoroacetate ion in green has 3 fluorine atoms, and of course acetic acid does not. And so we know that fluorine is very electronegative. And what's actually going on here is that those fluorine atoms are able to pull electron density away from the negatively charged oxygen over to the right. And so this pulling of electron density is a stabilizing effect. It's pulling through the sigma bonds and relieving the oxygen of some of the negative charge. And this is called an inductive effect when you get a through sigma bond pull of electron density. You can also have inductive effects where you have a through sigma bond push of electron density. In this case, we're looking at a pull. And so anytime you can pull electron density away from something that's negatively charged, that's going to help to stabilize that negative charge. These graphics here are called electron density maps, and they might help you be able to visualize how the electron density is spread out more when electronegative atoms exert an inductive effect. On the left is the ethoxide ion, which is just CH3CH2O-. And on the right is trifluoroethoxide, where you have CF3CH2O-. And you can see, looking at the Lewis structure here, that again, the fluorines are pulling away the electron density off of the negatively charged oxygen. And so the color indications here are that red is higher electron density. And you can see on the left, where you do not have this inductive effect, that the electron density is very localized around the oxygen. And on the right, the oxygen has been relieved of a lot of that electron density because it's being pulled through the sigma bonds toward the other end of the ion. To summarize, the inductive effect of these fluorine atoms are stabilizing the trifluoroacetate ion relative to just the acetate ion on the right. So we can say that trifluoroacetate in green is more stable than acetate in blue. Therefore, the more stable conjugate base, of course, comes from the stronger parent acid. And so we can say that trifluoroacetic acid is a stronger acid than acetic acid. There are a couple of other notes about the inductive effect. First, there is a correlation between the number of electronegative atoms present and the strength of the inductive effect. So if you take a look at this example, the difference between these two structures is that one has 1 fluorine atom on the top, and the structure on the bottom has 3 fluorine atoms. And if you take a look at the pKa values, having 3 fluorine atoms lowers the pKa from 2.7 to 0.2. So adding on those extra 2 fluorine atoms increases the inductive effect and therefore makes the compound more acidic. There's also a correlation between the identity of the electronegative atom and the strength of the inductive effect. So in the series that we're looking at here, fluorine is the most electronegative. As if you pay attention, this is going down the halogen series and we're getting decreasing electronegativity as you go down the group. And so fluorine is going to exert the strongest inductive effect. And if you take a look at the pKa values, you see that as the inductive effect gets weaker and weaker going down the column, the acidity of the acid actually is getting weaker as well. So again, more inductive effect, more pull of electron density equals stronger acid. And then finally, there's a correlation between the proximity of the electronegative atom to the site of electron density and then the strength of the inductive effect. And so this time the difference between these two structures is the location of the electronegative atom. When it's closer to where the deprotonation is going to take place, where the negative charge is going to form, then the inductive effect is felt more strongly. So having the chlorine atom closer, as in the yellow structure, makes the compound go from a 3.98 to a 2.83 pKa. So there is this increase in acidity. What I want you to try to do here is to pause the video and to try to pick out the most acidic compound from these 4 that are presented to you. The answer is circled in pink. So notice this time when the acidic proton comes off, we're not getting a negatively charged oxygen in all cases. So we have some compounds that contain sulfur and some that contain oxygen. So you have to look at elemental effects as well in this case. We can automatically rule out the 2 oxygen-containing compounds as being the most acidic because when you look at the sulfur analogs, we know that because of elemental effects, the sulfur-containing compounds will be the more acidic. Then between the 2 sulfur compounds, we have the same number of fluorines in there, but it's the proximity of the fluorines to the site where the negative charge is going to form that is really different. And so the closer those fluorines are to the site of deprotonation, the stronger the inductive effect that will be felt.